Hello, everyone. Welcome back. Okay, so we were just talking about periodicity, and the reason we were talking about this and other things like recurrence is because we want to talk about the limiting behavior of a Markov chain. Okay, so here I have a matrix, a transition matrix. I've got three states. Call them whatever you want. Let's call them 1, 2, and 3 because that's what these rows and columns look like. I happen to be in R. It doesn't matter. And the probability I go from 1 to 1 is 3/5, and then 1 to 2 is 2/5, and 1 to 3 is 0, etc. So what I'm going to do is take this matrix and square it. That's weird matrix multiplication in R, and I get this. And now I'm going to cube it, and I get this. Are you getting all those numbers down? You don't need them. Let's try the fourth power. Ooh, something seems to be happening here. Let's do one more. I think the columns are settling down to constants, like the first column to 0.53 something, and the second column to maybe 0.32 something, and maybe 0.14 in the last column. I would have to go a little further to be sure, but what we are seeing is the limiting distribution of a Markov chain. So if you have a Markov chain on the state space 1, 2, and 3, and you have the transition matrix that I started with here, then let's see, 1, 2, 3, 4, 5. This is the probability of going from 1 to 1 in 5 steps. And this is the probability of going from 2 to 1 in 5 steps. And this is the probability of going from 3 to 1 in 5 steps. And you can see that it's the same. So it kind of seems like if you run this for a long time, the probability you will end up in state 1 is around 0.53, no matter where you start. And the probability you end up in state 2, no matter where you start, is around 0.32. And it's around 0.14 for state 3, no matter where you start. So this is the idea of a limiting distribution for a Markov chain. Of course, the rows have to add up to 1, so these three limiting numbers will add up to 1. And so the idea is that if you ran a Markov chain that was nice enough to converge like this for a long time, you should be seeing the states that are visited settle down to fixed proportions. If you care, you can try it out with the matrix was, I mean, you can pick most matrices, but you might hit on one that doesn't converge to anything. But if you care, that was 3/5, 2/5, 0, 1/3, 1/3, 1/3, and 3/4, 0, 1/4. And so just start taking powers of it, and you should see the column settle down to constant values. So what we're looking at here is we want to consider the probability of moving from I to j in n steps, and then taking the limit as n approaches infinity. So kind of a limiting probability. And if I is transient, we expect this to be 0 because the transient states are the ones that have a possibility of escape. And if there's a possibility of escape, never to return again, if you run the chain for an infinitely long time, you will get there. So eventually you won't be at that state anymore. So what I'm saying is if I is transient, you should see that this limit is 0, which is not what we were seeing in the matrix that I was taking powers of before. And we know just from looking at this matrix right here that the entire chain is recurrent because all states communicate and it's a finite state space. So you can't possibly wander away from anything forever, never to return again. There's just no place to go. When this is interesting is when I is recurrent. That's what I want to talk about next, the recurrent case. So before I can tell you when this limit is going to exist and things that are special about this limit when it does, I do need to put in another definition, which is how you do problem 1 on the current homework that came out today. So here is the definition. And it is, if you have a recurrent state, we can break down its recurrence to like a strong kind of recurrence and a weaker kind of recurrence. I'm going to let I be a recurrent state. And then if the expected time until first return, so I'm saying return, which implies that I'm starting at state I. Okay, so if the expected return to I. So by saying return, I'm already kind of building in that I'm starting at I, is finite, then this is kind of strongly recurrent. We say in particular, it is positive recurrent. I is positive recurrent. And it could be that you have a recurrent state, so you will return, but it's going to take a really long time. And in fact, the expected number of steps is infinite. So you will actually return with probability 1, but it takes a long time. And so if the expected return is infinite, we say that the state is null recurrent. And so this is the topic of problem 1 on your homework 3, and I will say something about that. But first, let me state a theorem, and that is that these ideas of positive and null recurrence are class properties. So if states I and j communicate, either they're both transient or they're both recurrent, and if they're both recurrent, they're either both positive recurrent or null recurrent. So I put this proof in the, or I don't have my notes up yet. I was only ahead for one day. I will be putting this proof in the notes I'm posting today. You don't have to read it. It's kind of involved. You can read it if you're interested, but I'm not going to test you on it or really ask you about it. So it is a proof of that positive and null recurrence are class properties. I don't know if you think that's surprising or not. I'm not surprised that, say, recurrence is a class property. So if starting from a state I, you can return again, and you will return, then if j communicates with I, then starting from j, you can go to I and then come back to j, and starting from j, you can go to I and you can go off, you can return to I and then come back to j. So you can get recurrence for j out of recurrence for I. I think that the recurrence happens in finite expected time is maybe, I don't know, to me it's not as clear till you look at the proof. So I did mention homework 3, problem 1, just to get you going on that. Do you have a two-state Markov chain, 0 and 1, with probabilities 1 minus alpha, alpha, and beta, 1 minus beta? And in the problem, it says that alpha and beta are both strictly between 0 and 1, so we can't, we don't have any sort of weird periodicities or reducibility. And so part A says, show this chain is recurrent. And you don't have to do it this way, but I would show that G, first of all, I would say everything communicates because you are given that both alpha and beta are between 0 and 1. So you can get around this space. You're not going to get locked into anything. And so you only have to look at recurrence for one state. So I would pick state 0. And so we need to show this for state 0. So we have this G sub 0 as our notation for the probability we return to state 0 starting there in a finite amount of time. And I've already started using this notation where we write this as a sum of these probabilities of disjoint events, G0 super n, where G0 super n is the probability that the first return to 0, starting from 0, happens in exactly n steps. So given the nature of this chain, and just like you had another problem like this, and it only worked out nicely because the chain was so nice. Once you start writing these guys out, you'll realize that it's pretty easy to come up with a formula. In general, it's not if you have a lot of states and a lot of places to go. And so you want to show that G0 is 1, and that will get you recurrence. And then for part B, you want to show it's positive recurrent. And so you can use those same G's. So if we write, let's see, Ti to be the minimum for n greater than or equal to 1 for xn to be in state I, then we want to look at the expected value of Ti starting from I. Remember, this guy, this is the expected value of Ti given that x0 was I. Circle corresponds to the circle. So Ti is the time of the first return. So if you know the first return happens in exactly one step or two steps, if you can find those probabilities, then you can find the expectation. And so what I'm trying to say is this is simply the sum from 1 to infinity of n times the probability the first return is at time n, which is the G0 super n, which you will already have found from part A. Okay, so positive recurrence and null recurrence are class properties, and the proof is included in the notes and is optional. Sometimes I'll include the proof and I'll say, please read it. It's important that you read it. This one is not important, but I do want to talk about one particular thing that was used in that proof because we're going to need it a lot, and it's called Wald's equation. Okay, so this isn't what I'm about to write is not Wald's equation. It is the motivation. So suppose we have random variables, x1, x2, etc., that are identically distributed. They don't even need to be independent, but they usually will be independent and identically distributed. So suppose these are identically distributed. They're all gamma random variables with the same parameters, or they're all geometrics. So this means they all have the same PDF. And if you were to find the expected value for any one of them, if it was continuous, you would integrate x times that PDF. And if it was discrete, you would sum x times that PDF. And they all have the same PDF, which means they all have the same expectation. So suppose your x1, x2, et cetera, are identically distributed, maybe even independent, but I don't care. Then you all know that if you want to find the expected value as I goes from 1 to n of the xi, you can say that expectation is a linear operator and pull that sum out. And then you can say that all of these expectations are identical. So this is actually n times one of them because they all have the same expectation. The expectation of x1 or x5 or any one of them. This is not Wald's equation. This is the prelude to Wald's equation. So what is Wald's equation? This is, I don't know why I put that heading there because it's the topic we're in, but this is not actually Wald's equation. So this setup is, suppose that x1, x2, etc. are identically distributed. And what I want to do here is actually sum up a random number of the x's. And so I'm going to let capital N be a positive integer valued random variable. And I'm going to assume that it's independent of the x's. So then Wald's equation says that the expected value of the sum as I goes from 1 to this capital or random n. So don't write what I'm about to write because it's wrong, but you kind of might think it's n times the expected value of one of them, but that doesn't make sense because n is a random variable. It is in fact the expected value of n times the expected value of one of them. And this may be true in some cases where n is not independent of the xi, and we'll have to deal with that on a case-by-case basis. But Wald proved that if they were independent, then you can get this result. Let me give you an example of when it would definitely not be true. So suppose x1, x2, x3 are values of a Markov chain. No, even better. Suppose that x1, x2, x3 are IID, independent and identically distributed. And then you looked at like y sub n, which is I'm going to define as a sum as I goes from 1 to n of the x sub I. So this actually is a Markov chain. And if I wanted to find the expected value of y super n, that would be the expected value of the sum as I goes from 1 to the capital N of the xi. If I define the capital N to be the first time that that sum is 0, this guy would be 0, although there's y's in there. And then this would be some number of steps to get that sum to be 0. And this would be the expected value of any one of the individual things. And as long as that is not 0, I will not have the left side equal to the right side. So the proof of Wald's, I'm going to take the expected value of the sum as I goes from 1 to capital N of the xi, and I'm going to condition on n. So we've got a couple of random variables here. So I'm going to condition on n. This is the expected value of, this is the sum over all n. So I said it's positive integer valued. Actually, this would work if, for other subsets of n, but I'll stick with the one I have. The expected value of the sum as I goes from 1 to capital N xi, I'm going to move this down, given that n equals little n times the probability that n equals little n. So I changed this expectation to a conditional expectation. I multiply by the probability of what I conditioned on, and I'm summing over all those values. And you showed this formula in homework 1. Well, something very similar. So for the first expectation, because n is fixed to be little n, I get to replace this capital N with little n. So I get the sum as n goes from 1 to infinity. The expected value, the sum, I goes from 1 to little n, xi, given n equals n. And yeah, I didn't mean to write that again. So all I did between these lines is plugged in this lowercase n for this uppercase n, because I know the uppercase n is fixed at the lowercase n. So at this point, what the heck do you do with this? Because the n is assumed to be independent of the x's, I can drop the conditional part. Like we talked about this on the first day, it's kind of the same thing as the probability that x equals x given y equals y is the probability that x equals x if x and y are independent. And you can take that idea through an expectation as well. So I'm going to drop this, but I only get to do it because, number one, I don't need it anymore. There's no random capital N over here. And number two, it actually doesn't relate to the xi, because if the distribution of xi depended on n, then the expectations for each of these xi would be possibly different for each of the different n's. So I wouldn't want to drop that information. But I get to drop it by independence of n and the x's. Okay, so I've got, stop me if you need to. I've got the sum as n goes from 1 to infinity. I've got the expected value, the sum as I goes from 1 to n, xi, and I've got the probability, n equals n. And then you can run that inner expectation through. You can bring the sum out, and just like we did above, you can realize that that's n times a single expectation. So this is the sum as n goes from 1 to infinity of n times the single expectation times the probability that n equals n. And if you pull that single expectation out, we have what we want. We've got the expected value of x1 times n times the probability n equals n, which is the definition of the expected value of n. So we are done. There's definitely going to be cases where Wald's identity or equation will hold even when n is not independent of the x's. But they're going to be really specific cases. It's not going to be true in general. In general, we would need independence. So that was used in the proof that positive recurrence and null recurrence are class properties. An example would just be, this is kind of a stupid example, but suppose that we have x1 through xn IID, independent and identically distributed from the exponential distribution with rate lambda. So if you're not familiar with this distribution, check out the start of those notes, which is really that chapter 1. And there's also comments there about my notation for this. Most people write just exponential lambda, but by that they could mean that the PDF is f of x equals lambda e to the minus lambda x on x greater than 0 and 0 otherwise. Or they might mean that the PDF is identical to this, but with 1 over lambdas in place of my lambda. And so when I introduced the exponential in that chapter 1 of the notes that were supposed to be continuing, but instead I'm just doing modular notes, I go into this discussion about this um, because the exponential distribution is used a lot in Markov. We're going to start using it soon. And it's used to model times between successive occurrences of events. And so if you think of this x that I just circled as the typical inter-arrival time of a customer to your shop, if they're arriving with a rate of 2 per hour, the expected time for one customer to arrive is 1/2 of an hour. There's this inverse relationship between the mean and this thing called rate. And this one right here is where lambda is a rate parameter. And so that's why I write exponential with rate lambda to specifically say that I mean this PDF. And to keep it simple, I will always mean that PDF. If I want to talk about something that's exponential with mean lambda, I'll talk about an exponential with rate 1 over lambda. So this is really messy, but just to add on to this, the expected value of x here is going to be the integral 0 to infinity x times lambda e to the minus lambda x dx. And if you do an integration by parts, you're going to get down to 1 over lambda. So the rate parameter is inversely related to the mean. And then if you were to work with this one, you would get the expected value of x is lambda. So here it's called a mean parameter. All right, that was quite an aside. Check out the longer discussion in chapter 1 of the notes. So back to the example. Let me just start over. This is going to be a pretty contrived example, actually. So suppose we have IID random variables from the exponential distribution with rate lambda. And I'm going to let y be the sum as I goes from 1 to capital N of xi, where n has a Poisson distribution. Hopefully you've seen that before or reviewed it in chapter 1. And we usually use lambdas here, but I want something else. So I don't know, alpha. That's really weird for a Poisson. I will, when we get to the stuff where we need this distribution, I will review this distribution. But just to do this quick example, I'm just going to leave it at that. So the expected value of any one of these random variables is 1 over lambda because of the way I've set things up. And the Poisson distribution looks like this. It's going to be e to the minus alpha, alpha to the n over n factorial. And if you were to work out the expected value of n, oh, and this is for 0, 1, 2 on up, you would get the sum from 0 to infinity of n e to the minus alpha, alpha to the n over n factorial. And this is not hard to sum up. And I do it in that chapter 1, but you will get alpha. So the expected value of n is alpha. And so we've got that the expected value of y, which is the expected value of the sum as I goes from 1 to this random thing, xi, is alpha times 1 over lambda, or alpha over lambda. And this is assuming that the Poisson random variable n was independent of the x's. Can't really say anything interesting about this until we get just a little bit further into Markov chains, because what is going to be interesting is to compute expectations involving the Markov chains and random times of interest that we're going to look at the chain. So if we're looking at the chain at the first time it hits state 0, and we want to sum something up to that number of steps, that's when it gets really interesting and there's a lot of dependence going on. Okay, that was totally unsatisfying. So I've got a theorem for you, and it's one of um, several that I call the Pi theorems. So Markov people use the letter pi for lots of things. I am one of those Markov people, and I have four, possibly five, 4 or 5 important theorems involving an important distribution that's coming up now that we name pi. And I want to keep these theorems all together. In fact, I'm going to write them in their own document so you can have them all in one place. But for some reason that I'm trying to explain, I'm going to call this theorem pi 1. I really haven't had any sort of numbering of any of my theorems, so they're hard to reference. But these are the ones where I want numbers. So there'll be a theorem pi 2, a theorem pi 3, and a theorem pi 4. And it says this: for an irreducible positive recurrent and aperiodic Markov chain, so period 1, the limit as n goes to infinity of the probability of going from I to j in n steps exists and is independent of the starting value I. So back when I was taking powers of that matrix, the columns did not have to settle down to constants. The limit might not exist. The columns could just, all the entries in the columns could be all sorts of different things, and it's not approaching anything. Or we might talk about I guess we can talk about the limit for each row. Each row is going to correspond to a different starting value for your chain. So the first row, starting from state 1 and taking the nth power of the matrix, is sort of where you're going given you started from 1. And if it's not constant for each down the rows for each column, then the limit is not going to be independent of the starting state. So in pictures, if this is time and this is space, and we have a nice discrete time, discrete space thing, and we start at some state I, and we ran a Markov chain. Doesn't have to take one step at a time. This is no random walk. And we kept doing that out to time infinity. In the case where the Markov chain is irreducible, aperiodic, and positive recurrent, in the end, we'll get a point. That looks like I again, but we'll get like a J. And sorry, I didn't leave myself enough space, so here's infinity. If we started from I over and over again, we end up maybe here, end up here, end up here, end up here, end up here. There's some distribution out here. That's a limiting distribution if it exists. So when does it not exist? Maybe the chain, it has period 2. So you never get to settle down to anything because you're constantly jumping back and forth between like 2 regimes. Like if you can only find state 0 in an even number of steps and you start from state 0, then you're not going to see 0 as a result at time infinity if infinity is odd, which doesn't make any sense. So periodicity can mess this up. Reducibility can mess this up because I probably do mean if I start at odd, yeah, it all went to, it all turned to garbage when I tried to say infinity was odd. So I'm not even going to try to save that. But if you have reducibility, then the chain could get stuck in one part of the space versus another part of the space. For example, if you have something like maybe on four states that consists of 2 2x2 blocks and everything else is 0, and you can't move between those blocks, can't move between them, then if you, let's say 1, 2, 3, 4, if you start at state 2, you'll always be in state 1 or 2. And so if you did that for an infinitely long time, you'll get values 1 and 2 with some probabilities. But if you started state 3 and did it for an infinitely long time, you'll get 3 and 4 with some positive probabilities and the other states with probability 0. Okay, so we're going to prove this theorem, but not today. We're definitely going to prove this in class. And we're going to denote this theorem by the letter pi sub j, which is going to represent the probability we land at state j after an infinitely long time. So the notation, this is why I called this one of the Pi theorems, we're gonna take the limit as n goes to infinity of the probability of going from I to j in n steps. We're gonna call this pi sub j. This is a probability. It's much like p sub j, but it's so special. It's Greek. And this is provided the limit exists and is independent of I. That's why I'm calling this a pi theorem. This pi, these are probabilities that form their own distribution over the state space. So note that the pi's are all between, I'm going to use pi I now. I used I up as a starting point in the line above, but now I can call it pi I. They're all between 0 and 1 because they're all limits of sequences of numbers between 0 and 1, because all of these guys are probabilities. So that's one thing to note. And the other thing to note is that they do add up to 1 over the state space. So if you look at the sum over all j in the state space S of pi sub j, this is the sum j in S of the limit. And if you're down for doing some sloppy math today, this is the limit of the sum. And that sum is summing across the ith row of the n-step transition matrix. Oh, you're not seeing it. Pij super n summed over j is summing across the ith row of the n-step transition matrix. So starting from I, you have to go somewhere in n steps, even if it's I itself, and I is included in that sum. So this is the limit as n goes to infinity of 1, which is 1. Which makes this a probability distribution because we have these two things. One is they're all probability valued, between 0 and 1, and the other is they add up to 1. Questions? Oh. Yeah, this has nothing to do with 3.14. Yeah, pi. Or Louisiana's version of pi. Wasn't it Louisiana who decided to make officially pi 3 or something? And who needs an official value of pi for government? I don't really understand that. I'll have to check on that story again. That was a while ago. All right, just some more notation. If you're talking about pi over the whole state space, I just want to do it as an example. So if my state space is 1, 2, and 3, then we'll have, assuming this all exists, we'll have a pi 1, pi 2, and pi 3 that add up to 1. Sorry, I gotta go. I just gotta sit and watch this chat. I'm not teaching anymore. No, we'll get a pi 1, pi 2, and pi 3, and usually we denote it by a pi, which people rarely put a vector over this, sometimes bold notation, but it's like a row vector of the pi's. So when I talk about pi, I'm just talking about that distribution, not a particular probability from that distribution. Hopefully that makes sense. It will, because you're going to see it enough. Okay. So the limiting distribution is always stationary, and I'm about to define what stationary is. So here is the definition. So forget the limit. A distribution pi on a space S, doesn't have to be the pi that comes from a limit, is stationary if pi sub j is the sum over all I in the state space of pi sub I, Pij. So before we interpret that, I just wanted to say that if you are into denoting your transition probabilities as P of I comma j, then you might denote your pi's as pi of I. I mean, there are different ways to write this. But what this is saying is, this is like if your chain is in stationary mode. So I keep talking about things as if I was simulating them, because I think that's one of the easiest ways to understand them. So maybe I have 3 states, 1, 2, and 3. And we already talked about if I start at any given state and run for an infinitely long time, that we're looking for some kind of limiting distribution on those three states. But a stationary distribution is one such that if you start the chain according to a draw from this distribution, so suppose in this example, pi1 is 1/2, pi2 is 1/4, and pi3 is 1/4. So maybe you start here like half the time and here 1/4 of the time and here 1/4 of the time. That's supposed to look equal. So in simulation, imagine you grab a 1 half the time and you grab a 2 and a 3, each 1/4 of the time, and you run forward one time step according to the probabilities in a transition matrix that this pi went to, then it's stationary if it's going to maintain that distribution. Meaning if you did it over and over again, you would see in the long run, 1/2 of your results at time 1 at state 1, 1/4 of your results at time 1 at state 2. Because as of now, if you start a Markov chain with some distribution, like you have 3 values, say 1, 2, and 3, and you run it forward, you could get anything there. You know, maybe you see 3 most often, and then 2, and then 1. This is not stationary. So given the PIJs, those have to be given first, we can actually solve this thing known as the stationary equation, which is at the top of your screen, for the pi's to find a stationary distribution with respect to the transition probabilities. And we will. So one more interpretation of this. This is like the probability when this chain is in an equilibrium. This is like the probability that you're at state J, no matter what time step you're at. And that can be written as the probability you are at some state I in equilibrium, multiplied by the probability you move from I to J, and summed over all the places you could have started with. So this is kind of like starting with the distribution pi, moving one step, summing over all the starting values still gives you the distribution pi. I am going to get cut off today before we finish this. There will be tons of examples. This will make sense, promise you. So the last thing I guess I can fit in here is that every limiting distribution is stationary. Super fact. Every limiting distribution is stationary, which is why I use the same pi's. Ultimately, we're going to get down to, and by the way, they both exist and are both unique, and we're talking about one and only one distribution for the entire chain. So check this out. If I let pi sub j be the limit as n approaches infinity of the probability of going from I to j in n steps, then if I look at the sum as I goes over s of pi I, Pij, this is like the setup for the stationary equation. So this pi I comes from this formula, but this needs to be I. So this needs to be something else. So I can write this as the sum I in s of the limit as n goes to infinity of pk, it's arbitrary, to I, n, Pij. So I just plugged in this limit for the pi. And then if I know, extra mathy people are cringing, but if I interchange the limit and the sum, then I get the limit of the sum of the pki to the n Pij. And then by Chapman-Kolmogorov, this is equal to the limit as n goes to infinity of pkj super n. And since we assumed that that limit existed, then this is actually pi j. And I'm going to have to redo this. This didn't make a lot of sense today. But this equaling this is the definition of pi being stationary. So I didn't assume pi was stationary. I only assumed it satisfied this limiting condition. And we proved that it was stationary. So we proved that every limiting distribution is stationary. And I'm out of time. So have a few minutes to stick around, but thank you. And actually, I left already. You're on lag. So gone.
Thank you.
Bye.
What's up, Jazzy? Oh my! Oh my! Did you like that class?